my mic on? Yeah, it's on. Okay, sweet. So, all right, I'm assuming you know how to do the first one. The idea of the first one is that when you expand it, I'll just talk about it briefly. But when you expand it, right, this is what you get. So this is just using the formula. Use this p plus q at the top. It's just some integer made up of two other integers when you add them. It's going to be some integer to the power. So you always start with that power on the top when you're choosing the things. And then you keep going. So you start at 0 and you keep going until you get to, so there's a bunch of terms in the middle here which I've left out. That's why I put the dot 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 until you get to p plus q that you're choosing. And then the 1, well, this is the first term. The first term is always going to be, you start from p plus q and then you go down until eventually you get to 0. Whereas the x term, since it's the second bit in the binomial, that's going to start at 0 and then it's going to go 1, 2, 3 until you get to p plus q. Okay. Now, what's good about this is that the 1 is just, the 1 in every single term is just going to go away because it's just 1, right? 1 to the power of anything is just going to be 1. So when you times by 1, it's just going to, effectively, it goes away, okay, in each term. So the only thing you're left with is actually the p plus q choosing whatever you're up to. You start at 0, and then you're also going to be dealing with the x bit to the power of whatever you're up to, okay? The 1s go away. So that's where this came from, right? The first term is just 1. That's pretty easy to see. X to the 0 is 1. P plus anything choose 0 is 1. Okay, the 1 is obviously still a 1, so it's just 1 at the start. Then p plus q choose 1. We're up to 1 now. So x to the power of 1. Then p plus q choose 2. X to the power of 2. And you keep going until you get to that. Then that expansion over... So we've done this expansion, right? We've done this expansion. That thing is the same as this thing on here. Okay, we've expanded that bit. But then we've got to deal with this x to the q on the bottom. And we're going to figure out which term in this thing is going to be independent of x. So what that means, independent of x means just find the constant term, okay, the one where there's no x in it. So this thing that we just expanded, is going to be over, it's going to be over x to the q. And if you think about it, which term is going to cancel with that one? Well, it's going to be the one, think about how these behave, right? You have some constant that we found from choosing whatever that we have to do. The 1's gone, so you just get left with the x's. So it's going to be some constant, and then the x's are just increasing by powers of 1 every single time. Okay, so the term in this expression that's going to cancel with x to the q is just going to be when the power for x gets to x to the q, if you think about it. The rest aren't, because, well, they're not going to be the same as the power as the bottom, so they're just not going to cancel out, right? If you have x to the 3 and x to the 5, they're different, so they're going to cancel in some way, but you're going to get left with 1. So in this case, there's 3 in common in both, but there's still 2 left on the bottom. So you're still going to get an x term left. The only time you're going to cancel completely with the x's is when they're exactly the same. Oops. Okay, so you need to cancel them. And that's going to, since the x to the q is on the bottom, the only time they're going to be the same is when the top is x to the q as well. So what's going to make an x to the q term? Well, it's just going to be when we get up to x to the q, right? Because we start at 0, x to the 0, then we get to x to the 1, then we get x squared, x3, until you eventually get to p plus q at the end. So yeah, when you get to the x to the q term, that's going to be the one that cancels with the x to the q. And so, oops, quite hard to erase now. And so that's going to be the term. It's going to be the qth term, in a way, if you include the 0th term at the start. So that's going to be what it's going to end up being. And the reason for that is, well, let's find that qth term, right? The 1 bit is always just going to go away, like I said, but the qth term is going to be p plus q choosing q, and then the x is going to be up to q, and then that's going to cancel with the x to the q, so these cancel and you're just left with the choosing part, which is exactly where we end up with. So that's the first bit. God, it's so hard to... There we go. All right, then the second bit. Okay, so the second bit is going to need to use the first part. All right. So these things are connected. So Okay, notice that in the first part we found the constant term of that expression. We sort of ignored all the other terms, right? It was this whole thing. Okay, it was this whole thing over x to the q. But we only wanted to find the constant term, and so we only focused on that x to the q term, that one term, and because that's going to cancel with the x to the q on the bottom. So there's this whole thing here, but we only focused on one term, and that's what we ended up with. So we know what the constant term of that is, all right? And we just sort of ignored the rest of the non-constant terms, or so we call them non-constant terms or terms that are independent of x, okay? Or terms independent of x. Right, those are some ways that we say that. Okay, the rest we ignore, right? We're just looking for the ones that are constant. Sorry, yeah, constant, that are independent of x. The non-constant ones we ignore. So that's going to be helpful in this one, because what they're saying is this thing that we just found the constant term for, this thing is going to be equal to that thing. Now, the reason why this is equal to that thing, it's actually, it's hard to see it, but there's a way to show it, just using simple power laws, fraction laws, and all that stuff, and algebra. But just don't worry too much about it, okay? I could show you how it gets to there, but it's not a big deal, and you're not going to need to do it in this situation anyway, because they're giving you that, okay? But that is true, okay? Don't doubt that. That is true, and you can show that. I just won't in this question because it's not the focus. What are we up to? Yeah, okay, so that's equal to this thing. We have this new thing. And then they're asking this hard question where it's like, apply the binomial theorem and the result of part one to find a simple expression for this thing. And you might be looking at this thing, and you're like, well, what the hell, where did that come from? So connecting these things is going to be quite difficult. That's what's hard about this question. So this thing, well, first of all, let's try to they're telling us to do something. So let's do that first, okay? Now, the first thing I noticed, and it's probably good for me to let you know earlier on, is that you can actually sort of, alarm bell should be ringing when you have this term, because this term, right, there are no x's in it. These are just constants, right? It's 1, and then you're choosing something. These are just going to be constants. There's no x in there, right? In fact, this whole thing doesn't have any x's in it. So that's likely going to correspond with the fact that this is also something that's independent of x that we found in the first bit. Okay, that's going to come into play at some point. Now, we already expanded this, and we already found what the constant term of that is. Okay, so that's going to come into place at some point. Then this bit is new, and they're asking us to apply the binomial theorem. So let's do that. Okay, let's apply the binomial theorem for this bit. So if we apply the binomial theorem for this bit, there's two sections actually. You have that bit and this bit. So you have to do two expansions, one for that and one for that. When you expand the first one, you can go through it yourself. Hopefully you can expand these respectively. Okay, it's going to be 1 at the start, and then again, both of these have 1 in the first term, so the ones that are going to go away. You're just going to go left for the choose part, and then for this bit, for the 1 and x to the p bit, it's just an x. So x to the power of 1, x to the power of 2, p choose 1, p choose 2. That's just how it works. It expands like that. Then you have this bit, which is a very similar expression. It's just that there's a q now, and there's a 1 on x instead of an x. So the 1s are still going to go away. You're going to start with the 1, then it's q choose 1, so 1 on x to the power of 1, which is just that. Q choose 2, 1 on x to the power of 2, right? This 1 on x to the power of 2, the 2 just goes on the 1, so it's just 1, and then it goes on the square. That's how you get to just that. And it's going to be the same thing. So the interesting thing about these two expansions is that this one behaves where basically you're going p choose 1, 2, 3 until you get to the end, and then you have these x terms which just increase by powers of 1. So it's quite a simple expansion in a way. Same thing with this one. You still have those choosing terms, those combinatorical terms, just going 1, 2, 3. But now, instead of x's, we have 1 on x's, but they're also just increasing on powers on the bottom, right? You have 1 on x squared, 1 on x3, and it keeps going until you get to the end, okay? Now, you're then going to multiply those things. So you have this bit, and you have that bit. You have this expansion, and you have that expansion. When you multiply them, all right, you got to think, okay, how is that going to help me, right? Because that's going to be impossible to expand. I'm not going to multiply every single term with each other and expand the whole thing. That's way too hard. There's too many terms. It's a bit too general. But you don't need to do that, okay? You could, but you don't need to, all right? Now, the thing to notice here, and this is the hard bit about this question, is, okay, they're giving you this weird expression, all right? Again, notice that there is no x term in it. This expression, okay, there's no x term into it. So when I'm applying the binomial theorem in this part, I've expanded them. But then when I multiply them together, I don't need to worry about about any other term that's not constant. I just need to worry about the constant terms. Okay? Because, again, this bit doesn't have any x's in it. All right? I'm only looking at the section of this which is constant. So then you've got to think, okay, and the reason why I want to do that is because, again, there's no x term in here, and then also you're going to relate it to the constant term in there, okay? So, from the previous part. So, how can we find the constant terms in this expansion, right? We've expanded both, but then we need to multiply them. How are we going to find the terms that are constant? Well, if you think about it, right, notice what's generally happening in this expansion. There's just x's, okay, which range from 1, 2, 3 onwards. And then on this one, it's very similar. It's just that now there's a 1 on x, and that ranges from 1 on x, 1 on x squared, 1 on x cubes, and it keeps going. So the only real sort of difference between the x terms in this one and that one is that this is an x, but this is 1 on the x. This is an x squared, this is 1 on the x squared. So you're going to have to, like, if you're actually expanding this and multiplying them together, there's going to be a lot of terms. But we need to only worry about the terms which cancel out with each other because they're going to give us constant terms. So, for example, when you do a normal expansion, right, if I'm expanding that with this, you multiply everything. You go 1 with the 1, you go 1 with the 1, you go 1 with this one, you go 1 with that one, you go 1 with that one, all the way until you get to the end. And then you're going to have to do it for this one with that one, this one with that one, this one with that one, this one with that one. And then you're going to have to do it with that one and this one, that one and this one, that one and this one, that one and this one. And there's so many. But let's worry only about the ones where they cancel. And what are those going to be? Well, the first one at the start is going to be that one because 1 and 1 just make 1. Okay, cool. That's where this is coming from, by the way. And that matches up with this at the top. Okay, which is pretty cool. Then, so the 1 and the 1 make a 1. And then if you continue normally, you'd go 1 and 1 on x. But that's not going to give you a constant term because there's no x here to cancel with the x here. So it's just going to leave you with something times 1 on x. We don't want that. Okay, because that's definitely not going to appear somewhere here. So we just sort of ignore that for now. Okay, it's still included in the when you multiply this, which is why at the end, and this is why it's sort of hard to show things in this question, you write at the end, you say plus any terms that are independent, plus terms not independent of x, I should say, or constant terms. Non-constant terms, right? So the ones that actually still involve an x that don't cancel, they're going to be clumped somewhere here, but we don't need to worry about that. But we know that they're there. Okay? That's how you sort of structure this question. So, okay, 1 and the 1, that's going to go with there. 1 on x, not going to be there because of what I just explained. 1 and the 1 on x squared, again, not going to cancel with that. So we don't worry about that. And that's going to keep going. Because there's just going to be x to the something on the bottom, but this is just a 1, so it's not going to cancel. So the only thing that's going to be a constant is going to be the 1 with the 1, which is what we have here. Okay, let's do this one now, when we expand it with all these things. So this one with that one, well, if you put an x term with a 1, that's just going to leave you with an x, so it's not going to be constant. But then, this x with this 1 on x, the x's are going to cancel, which is going to leave you with a constant. And actually, what constant is that going to leave you with? Well, the x and the 1 on x cancel. But then that thing, PC1 and QC1, they multiply, which is what gets you this thing. And this is just writing it in a different notation. It's just writing how they wrote it above here. Okay? And then this x term with the other x terms, not going to cancel, because some things are going to cancel, like x and 1 on x squared. Some things are going to cancel here, but it's just going to be one of the x's that cancel. You're still going to be left with 1 on x. Same thing with here, x and 1 on x cubed when you get to it. X and 1 on x cubed, it's not going to cancel perfectly. Okay, you're still going to be left with 1 on x squared on the bottom. And that's going to keep going, because these are only going to increase. So the only one that cancels is x with the 1 on x. And I think you're sensing it. So that's where you get this thing. I think you're sensing a pattern here where the x squared is only going to cancel with the 1 on x squared. Okay, if you go with the 1 on x, or with the 1, for example, if you go with the 1, then it's just going to be x squared. If you go with x squared with the 1 on x, it's going to be x. X squared and x squared are going to cancel. X squared and x to the 3, 1 on x to the 3, they're going to cancel, but you're going to get left with 1 on x. Okay, and that keeps going. So this is going to only cancel with the 1 on x squared. And then let's look at what's left, the PC2 and the QC2, which is what we have there. In fact, I shouldn't put a plus there. Okay, that's where we got that. And that's going to keep going, right? So the whatever the PC3x cubed term is going to be, is going to cancel with the QC3 1 on x cubed term. And you're going to get left with P choose 3, Q choose 3. And it's going to keep going until you get to this end bit where the x to the p cancels with the 1 on x to the p. And you'll get left with the p to the p and the q to the p, just like they have up here. There's a reason why it's also q, but I'll explain that in a second, because I just want to get to the final answer bit. So anyway, this bit here gets to this bit. You find this expression when you're just looking at the constant terms of the expansion of this, as we've just shown. So since it's just going to be the constant terms that make this thing, okay, then since this expression overall is equal to this expression overall, well, we know the constant terms in this one was just equal to this. And we know that the constant terms in this yucky thing, it's the same overall expression, but it's just rearranged differently and overall, so it makes it a bit more complicated for the x. All the constant terms are spread out now. And then you've got to add them all up at the end. So all of them eventually will still add up to be this, because they're the same expression overall. So you say that this is equal to this because that's the same. This constant term needs to be the same as the constant term from here, from part 1, because these things are overall equal. Okay? And the reason why this is, so that's how you do this question. And the reason why this is like this is because they specified q is bigger than p. So this expansion here, this q bit over this p bit, this q bit is going to have a few extra terms, or an equal amount to p. It might be equal, but it might also have a few extra terms compared to the p. So all that's saying is you stop at the p bit. You don't keep going for the q's. You the p's from here will cancel with the q's from here, but you might have some extra q terms on the end, 1 on x to the something, where they don't have a p bit in here to cancel with. Okay. And those will just, so those won't be constant terms, and they'll just be included in this rest thing. Okay, so you stop at the p bit. That's what this is saying. Okay, you stop at the p bit. You don't keep going until q, unless p happens to be the same as q, in which case you stop at the same point.